This section is on value types and conversions. We are talking about value types. Each variable is associated with a space in memory. This space has a fixed size, and the size is associated with the type of data. Int and double types are examples of value types. And this means that the memory space holds an encoding of the complete data for the value of the variable. This is opposed to reference types that we'll talk about later. The fixed space means that an int cannot be a totally arbitrary integer of an enormous size. We can only hold an integer in a specific range. The smallest unit in a modern computer is a bit that has two states. You can think of those as just 0 or 1. Now, an int is held in a memory space of 32 bits. Each bit has two possibilities for a total of 2 to the 32nd power values. And they are encoded so about half are positive and half are negative. And as a result, the maximum value of an int is 2 to the 31st power minus 1, as you can see here, greater than 2 billion. And the minimum value is minus 2 to the 31st power, as you can see here. By the way, you certainly don't need to remember those numbers. They are named constants in C#. So in particular, this means int arithmetic does not always work. What is worse is that it fails silently. Look at this exchange copied from the C# program. First, I set the int I to be the maximum value for an int. And again, we see that maximum value. Then I have the expression adding 5, of course, which in math should be a larger positive number, but look what we get. Clearly, this negative number is not mathematically correct. This effect of doing arithmetic on a computer where the sizes are limited and then getting the wrong answer is called overflow. You really need to be careful if you're going to be using big numbers. Particularly, again, because this is silent. It shows no error. Just gives you garbage. Well, one way to avoid the issues with numbers that would mess up ints is to use the type long. The usage of ints and longs are identical, except that a long is stored in twice as much space and hence can handle much larger numbers. Now, the sizes of the storage spaces, obviously if you make them larger, you can store larger numbers, but there is also reason to use smaller versions. If you're going to have a lot of them, as we will see we can have when we get to the section on arrays, then the space becomes a real issue possibly. And if you know that all of your numbers have a modest range of values, then they can be stored in a shorter version of an int, for instance, a short. Talk more about that later. In this book, we're just going to pretty much use int and long. We've also discussed, at least briefly, the type double. So a double is also a value type stored in a fixed space. There are even more issues with the double type than with an int. Still, you have to worry about the total magnitude of a number if we get too large to store. But now we also have to worry about precision. Just think about it. Between just 0 and 1, there are an infinite number of real values. Clearly, we cannot encode for all of them in a finite amount of space. As a result, a double not only has a limited magnitude, it also has a limited number of digits of accuracy, or the precision. By the way, there is an older type, float. that takes up half as much space as a double, and hence has both a smaller range and less accuracy. But at least the existence of float gives us a reason for the name double. The name double came from the fact that its storage is twice that of a float. Another thing in dealing with large doubles is that enormous numbers tend to get written in a variant of scientific notation. For instance, scientific notation has something dot places beyond the decimal point times 10 to some power. This has an exponent, and we can't use that typography in C#, so we have a variant over here. In place of the 10 and the power, we have E, meaning 10 to the power of, and then we have an exponent. The exponent can be either positive or negative, but the whole expression here cannot contain any spaces. Now, the lack of error handling that we saw with the type int is not repeated with doubles. And if you are going to do scientific computing with enormous numbers, this could be important. Let's illustrate briefly. Unlike integers or ints, doubles do not overflow silently. There are values for infinity and minus infinity, and also not a number, which is abbreviated nan. Let's look at the C# transcript that I copied. Here I can start with x being the maximum value for a double, and here we see it printed out. You see this variant on scientific notation, more than 10 to the 308th power. And here I'm suggesting that y be 10 times as much as this maximum value. Rather than giving me some bogus negative number, it says, wow, this is really big, and the computer calls it infinity. Some arithmetic is legal with infinities. If I have an infinity here and I add or subtract a regular finite number, the result is still infinity. And it also makes sense to divide a finite number by infinity. You get 0. And if we subtract an infinity, we end up with minus infinity. So here we have z is minus infinity and y is plus infinity. Some things with infinities don't make sense. Adding plus and minus infinity, we can state it as the sum, but when we look to print out the value of the sum, we find this nan, not a number. In other words, that means there was an error. It could not do anything like a calculation. Furthermore, once a variable like sum has the value nan, if you try to do further modifications of it, like dividing by 1,000, the answer remains nan, not a number. This means that once you make an error, there is a lasting record of the error in the variable, or anything that you do with it. So it doesn't immediately bomb out, but it leaves you a record that there was an error. This is errors involving the magnitudes. Still, we have the precision issues with doubles, and the small inaccuracies in double arithmetic accumulating due to limited precision are not caught in any way. They still happen silently. So here's a summary now of some of the limits on these numeric types. Longs are stored in 64 bits and have this enormous range. Ints are stored in 32 bits, and as we've said, they have magnitudes up to greater than 2 billion. There is also a short that I just show you for comparison. It's only 16 bits, and so it only gets something over 32,000. And then for the doubles, they are also 64 bits. And we now need to look at both the magnitude and the precision. So we said this is the maximum magnitude we've shown before, and this is shown with about 15 digits, which is the amount of accuracy. And I just mentioned floats are only 32 bits, and they cannot handle numbers as large. See the smaller exponent here. And also there is much less accuracy, only about 7 digits. I mention those just for completeness. We're not actually planning to use those in this book. Another type, char. Char is short for character. A char literal is a single character but enclosed in single quotes. So here is the literal for lowercase a, the literal for $sign. Just as we needed an escape code for the double quote with strings, we need an escape code for single quote with characters, and it's formed in the same fashion. And we can use the same escape code to indicate a single new line as a character. Now, it's easy to confuse the size of the quotes. Single quotes around a single character give you a char literal. If we put double quotes around any number of characters, including a single one, we get a string literal. You can mess yourself up by confusing those. Now, I mention this mostly because of errors that you're likely to get yourself into and not understand. An individual character is technically a number. The numeric value is a numeric code given by the Unicode standard. Unicode codes are 16-bit, which means they can hold a lot more than the usual alphabet on our keyboard. They hold the alphabets of many different languages and also some special symbols. However, I mention this for completeness, we will stick to the standard American keyboard for characters. We'll come back to the idea of the character being a number later. Casting. We have this idea of types in C#. So while 42 and 42.0 are mathematically the same, they are not the same because of the different type in C#. Now, in various places, numerical types get converted automatically by C#. They can also be converted explicitly by the programmer. Let's talk about some of these situations. A major issue is whether the new type can accurately represent the original value. Now, first of all, going from int to double has no issue. Any int can be exactly represented as a double. Here's some example code, again copied from a run of the C# program. If I declare an int and give it a value 33, then I can declare a double D, and I can either assign it or initialize it with this int value, no problem. I can also assign to a double an int value, no problem. Also, I can do arithmetic combining an int and a double. The larger type is the double, the int is converted, and we're going to get a double result, as we can see down here. After I do show vars, we see that z ends up as 35.5. That's 33 plus 2.5. And here are the values that we got from the others. Now, the other direction for conversion is more problematic. Let's suppose we start with a double, which I initialize, declare an int I, and try the assignment. I want the int to get the value from the double. Well, you see the error that I get, that we cannot implicitly convert type double to type int. That's because the int I cannot accurately hold the values of a double, like the 2.7. Now, the compiler does this checking. It doesn't actually look at the value of the double. Even if I'd started with 2.0, which is mathematically the same as an int, I'm going to get the same sort of error here. Sometimes you really do want to lose possible precision and convert a double to an int. You have to then be explicit to avoid this error message, and you do this using a cast. That's the technical term that, by the way, was suggested in the error message here. So let's look. Again, this is starting the same code as we had before, where we assign a value 2.7 to a double D, create an int I. And so here I'm again doing an assignment from I using a value from D, but see what I have in front? The int in parentheses here, or another type, is a cast, an explicit cast saying that I want you to do, compiler, to do a conversion from double to int. Now be careful. If you think what would the conversion be, you might guess wrong. Here, where I let it print out the value of the int I, it is 2, not 3. This conversion does not round, it truncates towards 0, dropping whatever fractional part, in this case 0.7. You're more likely to want to convert by doing rounding, and this is a bit more complicated. It takes several steps. There is a function math.round, which will take a double as parameter. However, it still produces a double result, just one with 0 fractional part. So if you ultimately want actually an int to be rounded from a double, we need to produce the integer value, integer, not int, value, and then cast it to an int. This is continuing the previous example where D was 2.7. If we round it and convert it to an int, we see that I is 3. That's the normal way to round. You can also do an explicit cast from int to double, but as we saw, that gets done implicitly in general, so it's not needed. But there are places where you do want to do it explicitly. Here's an example. We would generally calculate a sum with some more major sequence of steps, but I'll make it short and just suppose sum is 14, an int, and like the number of terms that we added, suppose, was 4. We could calculate an average. We would want that to be a double, AVG. And, the mathematical way to write it would be sum divided by n. But now if I print out AVG, the average, well, it's not quite. 14 divided by 4 is not 3 in math. This is the integer part of the quotient because sum was an int and n was also an int. This operation is between ints and produces an int result, even though it is assigned afterwards to a double AVG. So in this case, recall if we want a double as a result of division, at least one of the operands needs to be a double. And so here we can put an explicit cast to double and then do the division. And then we get, mathematically correct answer. 14 divided by 4 is 3.5. There's a little subtlety here. We're not used to this in math, but this is an operation in C#. And like all operations, it has a precedence. It happens that the precedence of cas is higher than any arithmetic operation. As a result, it binds directly to the sum here. So this is the same as if we put in an extra pair of parentheses here, saying convert sum to a double, and obviously then divide by n. On the other hand, if we were to make it explicitly the other way and say cast to double, and then because of the parentheses now around the division, the result of the division, we still get a value of 3, because when we are doing this division, we are working on an int and an int, and we get an int result. We cast to double too late. By the way, there's an appendix for the precedence of operators showing all of them, a number of them that we haven't discussed yet, but they're all there, including the ones we certainly have discussed. I mentioned that the type char was technically an integral type, a number. The number associated with the character is the numeric code associated with its Unicode designation. But now there are various places you can get messed up. You might say here, quote A plus quote dash. You would expect perhaps to get an A dash or A minus, but you don't. You get 110. So what's happening? Modern computers work easily with the type int. It's harder to work with smaller types. So when you do an operation, and these are numbers, they are small numbers. They're the same size as a short, actually. But what happens is they are implicitly converted to int, the easy size for the computer to work on. So what we end up getting here is a sum of ints, and a sum of ints produces an int. If we look at these individually, we can cast them directly to see what their underlying numeric value is. If we take A and cast it to an int, look at its value, and we see that it happens to be 65. That's the code number for a capital A. Similarly, we can get the code for a dash and find that it's 45. And these two conversions are done implicitly in this expression here. And so what do we end up adding? 65 and 45, and we get 110. So that's why this answer. By the way, it's also possible to cast the number back to a character. Here's just an example. If I take A and add 1, that's going to end up being a number. Okay, I guess it's going to be 66. Well, I can cast it back to a character, and it then gets printed as a character since that's its type, and we get capital B. The capital B is the next letter after capital A. That makes sense. Turns out all the capital letters are in order in the code.